You know that feeling when an app is just instant and others feel clunky and slow? Well, the secret isn't always about your phone's power. It's about the invisible rules running the whole show. Today, we're pitting these rules, these algorithms, against each other in a showdown to see what really makes our tech feel magical or just frustrating. All right, let's just jump right in with a question. Think about it. When you search for a file, how does your computer sift through thousands, maybe millions of items and find the one you want in the blink of an eye? The source material paints a perfect picture for us. Imagine you're in a gigantic library, and I mean massive, and you have to find one specific book. The catch? There's no catalog, no signs, no sections, nothing. You'd literally have to look at every single book on every single shelf. That's the chaos your computer is dealing with. So how do we solve that library problem? Well, let's set up our first fight. It's a search challenge. In one corner, we've got pure brute force, and in the other corner, we've got brains. First up, our brute force contender, linear search. Its strategy is, well, simple. It starts at the very beginning of the line and just checks every single item, one by one. Is this it? No. How about this one? No? It's straightforward, for sure. No finesse, just pure grunt work. And in the other corner, representing the brains, is binary search. Now look closely at that first step, because it's the most important part. The list has to be sorted first. Think of a dictionary. Instead of starting at the A's, you just rip it open to the middle, right? Let's say you land on M. Is the word you're looking for before M or after M? No matter what you say, you just threw out half the dictionary. It's a super smart game of high-low that narrows things down incredibly fast. So let's look at the tail of the tape. Linear search's only real advantage is that it doesn't care if the list is a total mess. It just plods along. But binary search? It's a speed demon. It jumps through the data. But, and this is a big but, it has that one non-negotiable demand. The data has to be in order. This right here is one of the classic trade-offs in computer science. Which, of course, brings us to our next big challenge. If our fastest search method is only fast because it has a sorted list, then how do we get that order in the first place? How do we sort the chaos? Time to meet our sorting contenders. Our first sorting algorithm has a name that's pretty easy to remember: bubble sort. And yeah, as this quote suggests, it's named for exactly what it does. So here's the game plan for bubble sort. It just shuffles through a list, comparing two items right next to each other. Are they in the wrong order? Swap them. Then it moves over one spot and does it again. It makes pass after pass, and with each pass, the biggest unsorted items kind of bubble up to the end of the list where they belong. It just keeps doing this over and over until it can go through the whole list without a single swap. Now for our other contender, selection sort. This one has a totally different strategy. It doesn't care about neighbors. Instead, it scans the entire messy list to find the one absolute smallest item. Once it finds it, it plucks it out and sticks it right at the beginning. Then it just, ignores that first spot and does the exact same thing for the rest of the list. Finds the next smallest, puts it in the second spot, and so on. So here's the deal with these two. They're both pretty simple to understand, right? They make sense. You could probably do them yourself with a shuffled deck of cards. But they share a fatal flaw. Once you get past a pretty small number of items, they become painfully slow. They get the job done, yeah, eventually. So how do we actually officially grade these things? How can we prove one is better than the other? Well, it's not just a gut feeling. Computer scientists have a formal system for it, basically a report card. And that report card is called time complexity, and it's measured with this thing called Big O notation. Now, don't let the fancy name scare you. It's really just a way to ask one super important question. If I double the amount of stuff I have to sort, does the work just double, or does it get way, way worse? It's all about predicting how an algorithm will behave when things get big. And here are the grades. In this chart, n is just the number of items we have. So linear search gets a grade of O of n. That means if you have 10 times more items, it's going to take about 10 times longer. Simple enough. But check out binary search, O of log n. That log is basically code for unbelievably efficient. It means you can go from 1,000 items to 1,000,000 and the search time barely even budges. And then you've got bubble and selection sort. They get a grade of O of n squared. And that little squared symbol, that is a disaster. It means the workload doesn't just grow, it explodes. And if you're a visual person, this chart just says it all. Look at that. The O log n algorithm, our binary search, barely moves. The ON algorithm grows in a nice, predictable line. But the ON squared algorithms, that bar just shoots straight for the moon. It becomes unusable fast. To really put that into perspective, let's use some real numbers. On a list with 1 million items, a super efficient algorithm like binary search might take, say, 20 steps to find something. An O of n squared algorithm like bubble sort, it could take 1 million times 1 million steps. That's a trillion operations. One is instant, the other might not finish in our lifetime, no joke. Okay, but this isn't just theory for a classroom. This exact showdown, this performance battle, happens billions of times a day, and it shapes every single click and tap you make online. Think about calling a customer service line. You give them your customer ID. They've got to pull up your record from a database with millions of other people. But because all those IDs are stored in order, they can use a binary search. And the result? Boom, your info is on their screen instantly. That's what a good algorithm gets you. Smooth, fast service. Or how about online shopping? You're on a website and you click sort by price, low to high. That site has to sort maybe thousands of products right now. If it used something slow like bubble sort, you'd be staring at a loading wheel, and you'd probably just give up and go somewhere else. They use much, much smarter algorithms because a fast, snappy website directly leads to more sales. So here's the bottom line. Understanding this stuff isn't just for computer nerds. For the people building the technology we rely on, choosing the right algorithm for the job is everything. It is the fundamental difference between an app that feels like magic and one that is just plain broken. From finding a name in your contacts, to your GPS finding the best route, to the entire internet functioning, these simple, powerful ideas of searching and sorting are everywhere, quietly making our digital world possible. So that just leaves us with one last big question to think about. If these simple rules run the world we have today, what massive problem is just waiting for the next brilliant algorithm to come along and solve it?